Alright, let's go. Number 10. The Paradox of Youth. Yuri Levin and Alexander Beloborodov were not trying to solve a mystery about stellar birth. They were building models of gas dynamics near supermassive black holes, trying to explain ordinary accretion behavior at the center of the galaxy. Standard stellar formation theory says stars need cold, stable, undisturbed clouds of gas to collapse into a stellar core. Close to Sagittarius A, the black hole's tidal forces should shred any such cloud long before gravity could pull it together. No star should be able to form within roughly a light year of the black hole. What the data showed instead was a tight cluster of young, massive, blue-white stars orbiting well inside that supposedly impossible zone. Levin and Beloborodov, in a 2003 paper in the Astrophysical Journal, proposed that a massive gas disk had fragmented in place and collapsed fast enough to beat the black hole's gravity. Andrea Gaze's UCLA group, tracking these same stars through the Keck Observatory, confirmed their youth spectroscopically. Some no older than a few million years. The disk fragmentation model explains some of the stars. It does not explain all of them, and the timing required is uncomfortably tight. A competing idea, that the stars formed far from the black hole and migrated inward afterward, runs into its own problem. Migration this fast, without disrupting the star's orbits, has never been demonstrated in simulation. Astronomers call this the paradox of youth because there is currently no fully agreed mechanism for how something so fragile survives somewhere so violent. If the math is wrong by even a small margin, those stars should not exist. Every time you look up at the night sky, you're looking at proof that the universe occasionally breaks its own rules and never explains why. The paradox of youth is a nursery in a war zone. Number 9 is what happens to the corpse. Number 9. The missing intermediate mass black holes. Shunya Tekikawa and Tomoharu Oka were not hunting for a new class of black hole. They were mapping the chemistry of dense molecular clouds near the galactic center using radio telescopes, routine survey work meant to catalog gas composition. Standard black hole formation theory predicts a smooth ladder, stellar mass black holes a few times the mass of the Sun, and supermassive black holes millions of times heavier, with a middle rung of intermediate mass black holes bridging the gap, especially clustered near galactic centers, where dense environments should manufacture them. Instead, that middle rung is almost empty. In a 2017 paper published in Nature Astronomy, Oka's team identified a compact, cold gas cloud called CO 0.40-0.22, whose internal velocity spread implied something roughly 100. 0.00 times the mass of the Sun was moving inside it, invisible, radiating almost nothing. Not a star, not a supermassive black hole. Something in between, that theory says should be common, and observation says is almost never seen. Proposed explanations have piled up and fallen over one by one. Some argued the velocity dispersion was contaminated by overlapping gas streams, a data artifact. Not a black hole at all. Others argued intermediate black holes exist, but simply consume too little to glow, hiding by starving rather than by absence. Neither explanation accounts for why the population should be this sparse everywhere we look, not just here. If the theoretical ladder is wrong, we don't just misunderstand the galactic center. We misunderstand what your own body is ultimately built from, since every heavy element in you traces back through generations of stellar death that this same ladder is supposed to describe. A third possibility raised by theorist Marta Voluntari is that intermediate black holes formed early and abundantly, but merged so efficiently with one another that almost none survive alone today, leaving only faint gravitational fingerprints like CO 0.40-0.22 behind. That would mean the missing rung isn't missing at all. It was consumed by the very ladder it was supposed to build. If the ladder is broken, what else did we build on top of it? Number 8. The galactic center gamma ray excess. Lisa Goodenough and Dan Hooper were not trying to discover dark matter. They were analyzing publicly available data from the Fermi Gamma Ray Space Telescope, essentially doing routine background subtraction to clean up galactic center images for other research. Standard astrophysics predicts gamma-ray emission from the galactic center should trace known sources, pulsars, supernova remnants, cosmic ray interactions with gas, all cataloged, all accounted for. After subtracting every known source, Goodenough and Hooper found a smooth, spherical excess of gamma rays glowing at roughly 1 to 3 giga-electron volts, sitting almost exactly where theory predicts a dark matter halo should be densest. Their 2009 analysis, later refined by Hooper and Tim Linden in a 2011 paper in Physical Review D, showed the excess matched the expected signature of dark matter particles annihilating into gamma rays with almost eerie precision. Then, the failure parade began. A 2015 study led by Richard Bartels, using machine learning source detection, suggested the excess was actually thousands of faint, unresolved millisecond pulsars, not dark matter at all. But pulsar population models built to match that explanation require pulsar formation efficiencies higher than anything seen anywhere else in the galaxy. Neither the pulsar model nor the dark matter model fits cleanly. The signal is real. Nobody agrees on what is making it. Somewhere in that glow may be the first direct fingerprint of the substance that makes up 85% of all matter in the universe, including, statistically, some of the atoms holding your own cells together. A third camp argues the excess is a blend of both, a genuine dark matter signal partially masked by an unresolved pulsar population, which would mean the current data is simply not clean enough to separate the two, no matter how long we stare at it. Nobody has closed the case. The glow is still there, waiting to be explained. Number 7. The unexplained X-ray flares from Sagittarius A. Frederick Baganoff's team admit was not looking for eruptions. They were using NASA's Chandra X-ray Observatory to establish a baseline quiescent X-ray brightness for Sagittarius A, essentially taking a calm reference photo of the black hole doing nothing unusual. Standard accretion theory predicts a supermassive black hole this quiet, fed this little matter, should glow steadily and faintly in X-rays, with only gradual, slow variation over time. Instead, Baganoff's team caught the black hole spiking in brightness by a factor of 45 within about 10 minutes, then dropping back to baseline just as fast. Published in a 2001 paper in Nature, the flare defied the smooth accretion models built for low-luminosity black holes like this one. Since then, flares of comparable intensity have been recorded roughly once a day, some brightening by factors exceeding 100. Proposed explanations have not held up cleanly. Magnetic reconnection events in the surrounding plasma, similar to solar flares, explain some events but not the fastest ones, which brighten and fade faster than the plasma should physically allow. Infalling asteroid-sized objects being shredded near the event horizon were proposed by Fulvio Milia's group, but no debris signature has ever been confirmed. A black hole that should behave like a smoldering ember instead behaves, for 10 minutes at a time and roughly once a day, like it is trying to say something. A third proposal, favored by some theorists studying magnetically arrested disks, suggests the black hole's own spin is periodically twisting its magnetic field into a knot and then releasing it all at once. But the models built to test this still can't reliably predict when the next flare will hit. Whatever mechanism keeps triggering these outbursts is happening 26,000 light-years away, right now, completely indifferent to the fact that we still don't understand it. Number 6. The proposed dark matter spike. Paolo Gondolo and Joseph Silk were not investigating the galactic center specifically. They were running general calculations on how dark matter halos evolve gravitationally over cosmic time when a supermassive black hole grows slowly at their center. Standard dark matter theory predicts a roughly smooth, gently declining density profile throughout a galaxy's halo, thinning out gradually with distance from the core. Gondolo and Silk's calculations, published in a 1999 paper in Physical Review Letters, showed something different. That adiabatic black hole growth should compress the surrounding dark matter into an extremely dense central spike, potentially thousands of times denser than standard models predict, concentrated in a region just a few light-years across, sitting directly around Sagittarius A. If real, this spike should be one of the most dark matter-dense environments in the observable universe, and one of the best places to look for annihilation signals. 25 years of searching have not confirmed it. Some theorists argue that repeated close encounters between the black hole and orbiting stars would gravitationally scatter the spike apart before it could fully form, flattening the prediction back toward normal. Others argue mergers in the galaxy's early history disrupted it entirely. Nobody has directly observed the spike, and nobody has definitively ruled it out either. A weaker, softened version of the spike remains consistent with current gamma-ray and gravitational data, but weaker and softened is exactly the kind of answer that satisfies no one. It remains a theoretical prediction hanging unresolved directly above one of the most examined points in the sky, dense with a substance we still cannot see, touch, or fully explain. Number 5. The unexplained magnetic filament structures. Farhad Yousefzadeh was not looking for anything shaped like a harp string. He was conducting a routine radio continuum survey of the galactic center with the Very Large Array, mapping ionized gas as background work for other projects. Standard models of the interstellar medium predict turbulent, chaotic gas structures near a galactic center, no reason to expect large-scale order. Instead, Yousefzadeh's 1984 paper in Nature revealed dozens of thin, impossibly straight filaments of ionized gas, some stretching more than 100 light-years, running parallel to each other like strings on an instrument, aligned almost perfectly perpendicular to the galactic plane. Since then, over 1,000 of these filaments have been cataloged, some newly confirmed in 2022 survey work using the Meerkat radio telescope in South Africa. The leading explanation is that the filaments trace magnetic field lines threading through the region, illuminated by fast-moving electrons spiraling along them. But the source of electron acceleration remains disputed. Proposed triggers, supernova shockwaves, stellar wind collisions, black hole outflows, each explain a handful of filaments and fail to explain the rest, particularly the ones with no nearby energy source at all. Some filaments appear to have no cause at all, no nearby star, no remnant, no outflow close enough to account for the energy required to light them up. Yousefzadeh himself has continued studying the region for 4 decades and has yet to produce a single mechanism that explains the full population. The galactic center appears to be threaded with magnetic structure precise enough to look designed, and loose enough in its explanation that nobody can say why the precision is there. Number 4. The Fermi bubbles. Mung Su, Tracy Slatyer, and Douglas Finkbeiner were not searching for a hidden structure. They were studying diffuse gamma-ray background data from the Fermi telescope to characterize ordinary cosmic ray interactions across the galaxy. Standard models of galactic emission predict gamma rays should fade smoothly and symmetrically with distance from the galactic disk, following known gas and cosmic ray distributions. Instead, their 2010 paper in the Astrophysical Journal revealed 2 enormous, sharply edged lobes of gamma-ray emission extending roughly 25,000 light-years above and below the galactic plane, a bubble structure with edges too crisp for gradual processes to explain. The bubble's sharp boundaries imply a single, relatively fast injection of energy, not slow accumulation. Proposed causes have failed to converge. A burst of star formation activity a few million years ago could inject that much energy, but the required burst is larger than anything observed in nearby star-forming regions. A one-time accretion event onto Sagittarius A itself, a brief feeding frenzy followed by centuries of quiet, fits the energy scale but has no independent confirmation. A third hybrid model proposes repeated, smaller feeding episodes rather than one dramatic burst, but that version struggles to explain why the bubble edges are so sharp instead of gradually blurred by multiple overlapping events. Both explanations require our galaxy's core to have done something dramatic, recently, on a cosmic timescale, and then gone completely silent about it. The bubbles are still expanding. Whatever event created them happened after complex life had already existed on Earth for hundreds of millions of years, and we still don't know what it was. Number 3. The G2 gas cloud that refused to die. Stefan Gillison's team at the Max Planck Institute for Extraterrestrial Physics was not tracking G2 to test its survival. They were monitoring orbital dynamics near Sagittarius A, cataloging faint infrared sources as part of long-term stellar orbit surveys. Standard tidal disruption physics predicts that any diffuse gas cloud passing within a few hundred astronomical units of a supermassive black hole should be stretched and shredded by differential gravity, its structure destroyed on a single close pass. Gillison's 2012 paper in Nature identified G2 on a trajectory, bringing it dangerously close to Sagittarius A in 2014, predicting exactly that kind of destruction. Instead, follow-up observations through 2014 and 2015 showed G2 emerging from closest approach compact, coherent, and largely intact, its structure barely disturbed. A 2019 paper by Anna Cierlo and collaborators in Nature proposed the resolution. G2 was never a pure gas cloud at all, but a low-mass star wrapped in a dense, dusty envelope, its solid stellar core surviving where pure gas would not. That explanation solves G2 specifically, but a broader population of similar dust and shrouded objects discovered near the black hole since then, collectively called G objects, still lacks a full formation story. One leading idea is that these objects are the surviving cores of stellar mergers, two stars driven together by the black hole's gravity and fused into one dense body wrapped in the debris of the collision. But confirming this would require catching a merger in progress, which no one has done. Nobody agrees on how objects like this form so close to a black hole that should prevent their existence in the first place. Something near the center of our galaxy keeps surviving conditions specifically designed by physics to destroy it. Number 2. S2, in the orbit that shouldn't be readable. Reinhard Genzel's team in Germany and Andrea Gheza's team in California were not competing to break physics. They were independently tracking a single star, designated S2, to measure the mass of Sagittarius A through basic orbital mechanics, the same technique used to weigh any orbiting system. Standard Newtonian gravity predicts a star's orbit should trace a fixed, unchanging ellipse indefinitely, its shape locked in place. But S2 completes a full 16-year orbit around the black hole at speeds reaching roughly 3% of the speed of light, passing within about 120 astronomical units at closest approach, an environment extreme enough that Newtonian gravity should start failing to describe it accurately. The Gravity Collaboration, in a 2018 paper in Astronomy and Astrophysics, detected gravitational redshift in S2's light exactly matching Einstein's general relativity, not Newton's older model. A follow-up 2020 paper by the same collaboration detected Schwarzschild precession, S2's entire orbital ellipse slowly rotating in space, exactly as relativity predicts near extreme gravity, and exactly as Newtonian gravity says it should not. Both discoveries confirmed Einstein rather than overturning him, which sounds reassuring until you consider what it means. A star is tracing out in real-time physics so extreme that our best tested theory of gravity is only now being pushed to its actual limits. This close, this fast, this personally observable. And confirmation is not the same as comfort. Every increment of precision added to S2's orbit is also a test that general relativity could still fail, and every year astronomers keep watching for the deviation that would finally break it. Somewhere out there, a star is currently proving Einstein right in conditions no laboratory on Earth could ever recreate. Number 1. Sagittarius A itself. The Event Horizon Telescope collaboration was not trying to catch the black hole doing anything unusual. Their entire multi-year effort was aimed simply at producing the first direct image of the shadow of Sagittarius A, a technical triumph meant to confirm the black hole's size and shape against relativity's predictions. Standard models predicted a black hole this massive, fed this slowly, should appear as a stable, symmetric ring of light, bent around its event horizon, essentially unchanging on human timescales. The 2022 image, published by the Event Horizon Telescope collaboration in the Astrophysical Journal Letters, confirmed the ring, but comparing data collected across different nights revealed the ring's brightness pattern shifting noticeably from hour to hour, on timescales faster than the black hole's own light crossing time should easily allow. Since Sagittarius A is smaller and faster changing than any other black hole ever imaged. The failure parade here is not about whether the flickering is real, it's about why nothing fully explains its scale. Turbulent hot plasma orbiting near the event horizon accounts for some variability, but simulations consistently underproduce the speed and intensity of the changes actually observed. Magnetic instabilities in the surrounding accretion flow have been proposed and partially fit the data without resolving it completely. A third possibility, that our models of general relativity near an event horizon are themselves slightly incomplete, remains on the table precisely because nothing else has fully closed the gap. What we photographed for the first time in human history was not a static object. It was something changing, unpredictably, on a scale faster than physics comfortably allows, sitting at the exact center of the galaxy that contains every person who has ever lived. That is the shape at the center of everything we are part of, and it will not hold still long enough to be fully understood. None of these 10 anomalies sit at the edges of astrophysics. They sit at the center of it, literally, at the literal center of the Milky Way, inside the theories we trust the most: general relativity, standard stellar formation, standard dark matter halos, standard black hole accretion. Every failed explanation in this list was proposed by serious scientists using serious data. And every one of them fell short. The universe is not confused about what it is doing 26,000 light years from here. We are the ones still working it out. If you want to see more videos like this, click the video on screen now.